Hello again, it's Jesse here, congratulating you for the completion of lesson 2.4, in which we looked at the cyclic nature of the sun and solar activity. Now, this is one of the most important factors, the most important long-term factors to consider when it comes to aurora forecasting. Because the sun has this cyclic nature, the solar wind levels go up and down over the course of about 11 years, and this can really affect what we do or don't see here on planet Earth. So it's a very important consideration. Now, we started out by seeing that solar activity is cyclic. The amount of coronal mass ejections, the amount of solar flares is cyclic. It peaks and troughs every 11 years or so. But one complete solar cycle actually lasts 22 years, approximately, not 11. And that's called the Hale cycle. Now, the reason for this is because every approximate 11 years, the poles of the sun invert. North becomes south, south becomes north. Therefore, it takes double that time for a north pole to return to a north pole again, or a south pole to switch to north and then back to south again. So we say one complete solar cycle is 22 years, the Hale cycle. But it's safe to think as solar activity peaking and troughing 11 years, because us humans, us aurora chasers, we don't really care whether the north pole's north or south, as long as the sun's nice and active, as it is there in that picture by the Solar Dynamics Observatory. So when the sun is nice and active at solar maximum, we get lots of these things, lots of coronal mass ejections, lots of solar wind, and lots of aurora on planet Earth. And in the next lesson, we're going to learn about all of the mechanics behind the generation of that aurora as the solar wind interacts with Earth's atmosphere. So as aurora chasers, this is what we want to see on the sun. We want to see a lot of these things, a lot of CMEs, a lot of coronal mass ejections. But unfortunately, the sun also does this. Now there, I'm sure, as you can tell, the sun looks quiet. There aren't many magnetic prominences, there aren't many sunspot regions, there's not many CMEs, there's not really a lot happening. This, as I say, is what we want. All of those looping prominent regions are associated with sunspots. A lot of them will be flaring, a lot of them will be kicking out CMEs, and a lot of solar wind. This graph really nicely details the cyclic nature of the sun. It's nicely titled The Secret Heartbeat of the Sun. And those peaks and troughs that you can see there cover the average daily sunspot area of the visible hemisphere of the sun in a percentage. And we can also see that as time moves along from the late 1800s, when people started counting sunspots, every roughly 11 years the number of sunspots peaks and troughs like so. And you also might notice that outside of that cycle, the Hale cycle, there is a greater cycle. In 1960, the solar maximum was extremely exaggerated, as opposed to 1880, when it was not so exaggerated. And yes, if you're feeling a little bit pessimistic, you can see that the rough trend of this graph is that for the next solar maximum in the mid-2020s is going to be a more mild solar maximum. Don't let that put you off. That is still solar maximum. That is still a lot of sunspots, a lot of CMEs, and a lot of aurora on planet Earth. So there's a quick look at the cyclic nature of the sun. Another thing we're going to cover, recap on, is the heliosphere, the giant magnetic bubble that permeates the solar system to the edge of the solar system. You see, the solar wind moves through the solar system and eventually pushes against the heliopause, against interstellar space. The solar wind carries the sun's magnetic field with it. So we can say that the solar magnetosphere and the solar wind permeates the entire solar system. In the inner solar system, near Earth, it's referred to as the heliospheric current sheet. And this sheet, as you can see in this animation, is crinkled. It's rippled like the skirt of a ballerina spinning round and round. The reason for that is that the sun's magnetic poles are located differently to the sun's north and south axial poles. So as the sun spins on its axis, the magnetic poles point in different directions, causing this rippled effect. Now, the heliospheric current sheet is also referred to as the interplanetary magnetic field, or IMF for short. And the magnetic field on either side of these ripples and these crinkles is polarized differently. On one side of a ripple, typically it's got a southern polarity, and on the other side of the ripple, it's got a northern polarity. And as Earth orbits the sun and passes through these ripples, aurora can often be triggered. And we're going to learn why later, but it's to do with the fact that a southern polarity in the interplanetary magnetic field is more favourable by far for triggering aurora on planet Earth. Also, in these regions, in these crinkles, we have a lot of fast-moving solar wind as opposed to slow-moving ambient solar wind. And what you'll find that often happens is that a fast-moving stream of solar wind can compress the ambient solar wind, increase the density of the solar wind. It's also moving nice and fast. And again, as we'll see later on, that can trigger big aurora. And this sheet, this heliospheric current sheet, is by far more rippled around solar maximum. So understanding the cyclic nature of the sun can really help you predict what you do and don't see in the long term when it comes to the aurora. At solar maximum, we have more solar wind, more CMEs, more flares, more sunspots, but we also have a more textured, crinkly interplanetary magnetic field, again, triggering more of this, triggering more aurora. And in the next couple of lessons, we're going to learn why that is, how the solar wind interacts with Earth's magnetic field, and why we see what we see in the sky. So I'll see you later on at the end of the next lesson.